So thank you, everyone, for being there this morning. I'm sorry we are late, and we had also some train issue, location issue, and then computer issues. So we are now starting with a little bit of delay, but it's my pleasure to introduce Dr. Georg Glaeser. I know I don't say the right way. So you got your PhD from Ilmenau University of Technology, and you currently work with the IMMS Institute for Microelectronic and Mechatronic System in Erfurt. You are the team lead of the digital IC design and design methodology, and works on different IC design in the field of image sensor and ultra-low power RFID systems. Your research covers the design methodology for digital and mixed signal circuits and the application of artificial intelligence-based method in this field. So your field of work is very relevant to all what our PhD or doctoral candidate, I must say, are working on. So I thank you very much for this lecture. And work package 1, 2, and 3, certainly we learn and we are happy. Thank you very much.
Okay, thank you for the introduction. I'm happy to be finally here. Sorry for the delay. I'd like to keep this as interactive as possible. So I had really the challenge to compress this whole topic in this time frame. I won't go into every detail, but if you have questions, examples, just tell me, interrupt me. That's completely fine, and I'm looking forward to it. And there will be also a little bit of space for that. And I would rather skip some of my slides to answer your question. Okay. Before I start with the real content here of FPGA-based sensor signal processing, I want to tell you a little bit about where I come from. So our institute has the whole topic. We try to connect the digital to the analog world. You know about the mega trends of digitalization, but still the world stays analog, no matter what we do. And we, as the IMMS, are a land-owned research institute in Thüringen, Thuringia, from Ilmenau, and you have the task to strengthen SMEs in particular. And we are offering research-oriented, application-oriented R&D in microelectronic systems engineering and mechatronics. And in our department, where Eric Schäfer and I are coming from, it's centered on microelectronics. We are located near the Ilmenau University of Technology, and I'm working in the branch office in Erfurt in the Center of Microelectronics in Thüringen. So that's near XFAB. Maybe you've heard of XFAB. It was a semiconductor manufacturer. They are located here in this building, so they are right our neighbors. Okay, we try to bridge two worlds, the digital world and the analog world, the world of IT systems and Internet of Things, virtual processors, whatever you might imagine about digital things, with the analog world where things get physical, biological, chemical, whatever. And this means we have to bridge basic research to customers and industry. So we are trying to keep focus on applications while having one foot into research and the other in industry. We have some new applications, and we target the markets of life science, automation, industry 4.0, and so on. I won't read everything of that since we are short of time. The message is we focus on different scenarios here. And what we are talking here about are sensor systems. And that's also where parts of my talk come from. Just some statistics, we are nearly 100 employees, some PhD candidates, many students from different nations and so on. So I think the numbers speak for themselves. So that's our team in microelectronics. We have specialists for analog IC design, digital IC design, for mixed signal verification, which is also a field that's of growing importance for us. Specialized layouters, people caring about design methodology and EDA support. And normally our colleagues have degrees in electrical engineering, IT, microelectronics, engineering, computer science, biomedical engineering, and so on. And we're working at a pace of 10 to 15 ASICs per year for R&D. Yeah, and of course we have something around up to 15 students at the moment. We are very happy about that, to have them in our team and work with them together.
What is IC?
IC means an integrated circuit.
Okay.
So those like tiny things you have in your phone, for example, that do signal processing, signal acquisition, and so on.
And an ASIC is an application specific.
Okay. So that's it for the introduction of my institute. I know I fast forwarded a little bit. I hope I can catch up with the time frame somewhere in between. So about FPGA-based sensor signal processing. Before we dive into the topic, I have some questions for my first part, which is about introduction to basics. So, but before that, I have to do a little bit of expectation management here. So we will have a look at what is actually an FPGA, what are we actually talking about here, about structures for implementation, a little bit about verifying your design, and best practices for Verilog design, so what to do right or what to do wrong, and common pitfalls. So that's more practical things. I try to get it somehow to the level that we have some basics and also things that might actually help you in a design. So the second part will be more focused on things you might probably want to read before starting off your first FPGA design. But I had to exclude some items. So how to write Verilog, for example. So the programming language course, I just can't do in this time frame. There is a lot of literature about that. I have some pointers in the slides that you can follow up. And there's also a lot of stuff on YouTube about that. Also about high-level synthesis. That's something I cut out, even if it's relevant sometimes for signal processing, because it's an efficient way to get your algorithms to an FPGA, but you need to know something about the basics first, otherwise you won't be really able to use it. So, and also the synthesis algorithms, how this works. It's a really interesting topic to speak days about it, but that's not the day here. So, but before we start, just some things for me to know you. Now you know me, so I want to know you a little bit. Who played actually with hardware, for example, with Arduino microcontrollers? At least a few. A little bit, that's fine. Do we have here computer scientists? So pure computer scientists? Cool. Electronic engineers? Hardly. Okay. How about the rest? From which direction are you coming from?
Civil engineering.
Civil engineering, okay.
Physics.
Physics.
Mechanical engineering.
Optical.
Photonics.
Okay. That will be a challenge to explain things. So who has actually experience with VHDL or Verilog? Yeah, at least a few. And okay, so the point is, some of you will know many of the things I show in the first part, and some of you might not understand everything of the practical things in the second part. That's just due to the wide range I have to cover here, or I want to cover. So maybe that's showing you something where to follow up if you come into the situation where you have to deal with an FPGA. But if you have questions and want to get into this further, just ask now, ask later, drop me an email, that's also fine. So just to go into this, what are we talking about? Just try to get this thing a little bit reorganized here. Is there a possibility to
I think you can, if you say more, you can say add more. There is something for the add something.
Okay, what is an FPGA? So FPGA stands for Field Programmable Gate Array. Imagine this as a large structure of logic gates. So basic logic switching elements. You might have heard eventually in your way back in basic lectures that every logic circuit can be composed out of NAND gates, for example, or out of basic elements. And an FPGA is, from the bird's eye perspective, just a piece of silicon where you have many of those gates and basic elements with programmable interconnects. And the cool thing about this is that you can realize nearly arbitrary logic functions in it, which are running in parallel and which can be really fast. You can realize, for example, control algorithms which react in with a frequency of several hundred megahertz. If they are fitting in this timing budget, you can model a processor there. So create your own microcontroller which with application-specific instructions if you need it. That's all possible, and just a question of effort you want to put in this. And if you want to program it, that's normally done using specialized languages, which are called hardware description languages, like Verilog and EHDL. That are the most common. They work nearly as programming languages as Python, but you have to get used to some things. So many things run in parallel, and you have to synchronize things and so on. And there's, for each FPGA vendor, there's a specialized software that you can use for programming, for doing the synthesis process and so on. And since the application range is quite wide, there is a lot of documentation and also tutorials, entry-level things, and so on. And what's also nice is there are FPGA systems which have on-chip CPU on board. For example, this board we see here on the left-hand side, that's a board from Xilinx. There's the FPGA in the middle, and this FPGA has a dual-core ARM processor aboard and a freely programmable logic array. That's quite cool, since you can just offload things from the CPU to the FPGA area if you want to go for some faster processing. So the question is now, why and when is it useful to go for an FPGA? So the pros are it's inherently parallel. So logic gates just work in parallel. Physics does this job for you. It's very fast in calculations without the von Neumann bottleneck. So as long as the data is there, you can be fast. You can process things in parallel with many cores, as long as you can supply them fast enough with data. The processing can be in real time or even constant time. And you have a very fine-grained control about microarchitecture on how things are realized. We'll see an example towards the end of my first part. The cons of those things are you have less available memory. So normally you have just a few kilobytes on the FPGA itself, so that's not much. And accessing external memory can be tremendously expensive from the point of energy and time consumption or latency. The design effort is quite large compared to software, and turnaround time may be an issue if you have a compile process which takes several hours, which is no problem. I tried to depict it a little bit. We have a sketch for that. So you have those triangles here. If you go for high cost, you have a lot of money you want, but you need the performance, and you can afford having low flexibility, then you would go, for example, for an own custom chip or a custom processor that you design. If you want to have a very high flexibility, you have less money and you can deal with just okay performance, you can go for a CPU. And FPGAs can be somewhere in the middle. But of course, there are other application-specific processors, as for instance, hardware accelerators, GPUs, and so on. They are quite here. It's not that clear where to put them, since it's highly dependent on the application you want to go for. And FPGAs can be a solution for a special case that's not yet covered here, or where you have to deal about timing constraints and so on.
What is a TAT? TAT?
Turnaround time.
Turnaround time.
So the time you need for changing something in your design and testing it out and doing a full iteration loop. So now I created a small decision tree. Should I go for an FPGA? So you might think, yeah, cool, I want to do this. So just as a small hint, whether it makes sense or not, I created this one. Though the first is, if we just shortly go through it, you have to know those hardware description languages. If you don't have the time to learn them, it's sometimes a little bit harder to learn in normal programming languages. Since they have some, let's say, interesting quirks sometimes. If you don't have the time, just keep out of FPGAs. If you have the time, it can be really cool. Then you should be aware of that you have to restructure your algorithms a little bit to make them fitting, for example, to data stream processing. That you can formulate your algorithms by means of finite state machines, processing elements, and so on. We'll come to this in a second. You need to know if you can deal with less memory that you have on your FPGA. Then you should install your design environment for an arbitrary FPGA and try to get along with that. Get some examples running, and also the simulations, because simulations are also quite important here. If you tried VHDL and Verilog first and just synthesize something to an FPGA for trying to let an LED blink or something like that, you can do this. You can reach complex design, but you will have a hard time in debugging. So simulation is important. Okay, so since the question will arise where to start, if we want to learn something like that, I put some links here. That's just out of my personal collection, things that I found useful. FPGA for fun, it's more practical things, design examples. The second one is a book where it's something like this book by number of pages, but the first 200 are interesting, the rest is overview. And then there are some tutorials, and the last one is about specialties in hardware design. Also, if you want to know something about hardware architecture, the books by Tom Shenley are quite good. Why still, if you see the name ESA system architecture, is about old processors, but the explanations are really good and instructive. Also, clean code and clean architecture. And of course, have a look at your documentation of your favorite FPGA design tool. There's some more. If you have trouble with timing cases, constraints, want to verify with Python, need open source simulators. And what I want to highlight is the last one. That's an MSP430 microcontroller implemented in pure Verilog. And it's on GitHub. And the guy who wrote it is with Apple now, I think. He did a really good job in just writing good, clean, synthesizable, and very robust code. If you want to have a good example, that's the way to go. So, before we dive deeper, just some terminology. When I talk about a module, I mean an arbitrary entity in hardware. A device under test is a module that I want to exercise with some tests and see whether it works. A test bench is the actual module, as you see on the right-hand side of the screen, that puts some stimulus values to the device under test and checks if the output is correct. And of course, there's a scheme of there's the construct of a clock. So a signal, globally available reference signal that just gives a time reference to your system, and well, also an event reference. So it's a signal that goes up and down, and you time everything on, for example, the rising edge of the clock or the falling edge, and that's used just to keep the system synchronous. So how does the design flow work? So normally if you do this in several steps, you start from a specification where you write down what your FPGA should actually do, how the interfaces look like, something that's mostly worth a lot of effort to specify your interface correctly, which internal parts you need, which components, and which FPGA chip you want to target. The second step, you go for HDL coding. You have to verify your design, of course, in simulation, and then you go to the automated design processes of your FPGA design tool, which is then synthesis, place and route, and generation of a bit stream that you can program to your FPGA. And then afterwards, you can test in a real world environment and see what happens there, if your design fits your need. So that's also something I meant with larger turnaround times, because the cycles can be quite long, even if they are not that long as in the ASIC world. So now I want to go a little bit more into an example-driven explanation. I just created a small piece of Python code here to average over measurements, just as a simple example. Of course, each measurement comprises n samples, and I want to get out of it. Let's talk about what should we do to get this into an FPGA. So what we need interfaces. How do we get our data in? How do we get our data out? How do we store our data? Which processing elements we need? It's also an interesting question. And since we are creating hardware, as I said before, we cannot have infinite memory. This Python code is cool because I can just at runtime define how much memory I need, how much samples I have in my measurement. That's something you have to define beforehand if you're going for an FPGA. And you cannot dynamically increase during runtime. That's just not possible, so we have to fix this, or at least limit it at some maximum value. So we just modify our code a little bit, and for example, we tell it that it just works up to 128 samples. Have to remember how many samples we take, and then adapt our routines accordingly. That is the first step. Then we have to step out a little bit to define our interfaces. Because normally, if you write Python, you have your data already in memory. That's not true for FPGAs. So just assume that the data originates from whatever ADC or analog to digital converter, which is connected to your actual sensor. From there, we get a data, which is aggregated first, since we want to have a full measurement, and then average over the measurements. And then we go to our averager circuit or module. Here we have a data stream. Normally the ADC delivers data in a sequential way. And here we have just some packed form of data, however this looks like. Now we need to estimate a little bit about our system. How much memory do we actually need? Does it fit to our FPGA? We need to aggregate n samples and pass them to the averager unit. And the averager unit again holds n samples for storing the data. Since normally you have a large number of samples, you should try to reduce this. And of course, it would be cool to work directly on the data stream, which comes from the FPGA. So we just have to count the samples, and then we know on which point to store it, and we have to ensure somehow that the measurement is always completed. Seems simple, but already reduces our memory demand by a factor of 2. Okay, this means we adapt again our code and just work on a sample-based fashion. So we need to, of course, now modify the second routine. We are not adding a full measurement, we are adding a sample at the right position in our sample memory, in our measurement memory. We have to keep track on which sample we're actually looking at and where to put this in memory. Okay, now the question is, how do we get data from the ADC? So I assume something really simple here to make it understandable. Normally, if you go for something like this pink board, you will have XI streams. XI is a bus protocol. I won't cover this here. I just go to a very simple fashion. You get data on one bundle of wires, and on the second one, there is a valid signal which tells you, okay, now I can sample my data. That's a very simple way to put it. The readout, I assume to happen, that only happens when the measurement is done. So I don't have to care about collisions. So in a real world, you would have to regard the case that someone wants to read out your data while the measurement is not yet finished. And I'm not showing something about configuration registers on how to set, for example, your number of samples. That's something you would either hard code or make configurable using some register on some internal CPU bus. Okay, so now we are going for two implementation ideas. The first one is a finite state machine. So this means we want to describe our algorithm by means of transitions of some internal state of the algorithm. I assume a structure like this here. So we have a control state machine. We have some clock RAM. So this means on-chip memory for the FPGA. You have some counters and some unit that cares about the readout. So, and now we go for a finite state machine. So that's a common pattern for hardware description. We just assume there's a unit that updates its own state at each given clock cycle. And it's more or less, think like a step-by-step description what's going on in the system. And what we are drawing here is just a sketch for the implementation. And we can already use this for performance estimation by means of the throughput of data, for example. Yeah, so we start from some idle state. Also keep in mind, you have to define your start state. Eventually, somehow the measurement is triggered. Then we need to initialize our counters to see in which position in memory we are at the moment. Then we wait for a sample from the ADC, which is signaled using this valid signal. Once we have this data sample from the ADC, we read out the corresponding value from RAM, perform the averaging, write the value back to RAM, update the counters, and then we have to just see, is our measurement finished, or do we have to wait for the next sample and decide whether we go back to idle or not. It seems quite simple, but that's the way on how you describe hardware. So normally also your CPU in your laptop and your phone contains a lot of those patterns. You might think, okay, we have modern compilers and modern software. Why can't the computer do this for me? I have to tell you, it might be possible, but that's not there yet in the hardware description language world, or it's not. It has not made it to industrial tools yet. So we still stick to those descriptions or generators of them. So how to estimate something on this, for example, throughput. So throughput means how many data samples can I apply per clock cycle? Or how many clock cycles do I need for processing a single data sample? It can be also described in terms of processing latency. Let's assume that we have one clock cycle per state transition. So this means if you just count from here, we wait from a sample from the ADC and we go one round, we need 5 clock cycles. So we have a maximum data rate of clock frequency over 5. We can't get faster. But sometimes there are scenarios where you have to go faster, where you have to acquire data, for example, on each clock cycle, because your calculation takes too much area, it's too slow, and you have to reduce the clock frequency, or for whatever reason you want to be faster. There could be a second idea to go for a more parallel implementation, which is the pipeline version of that. So there, the idea is that we use independent units for each processing step, but we, of course, that's not for free. We have to post some prerequisite, and it's a little bit more difficult to implement. We need a dual port RAM, so a memory with two interfaces where you can read and write simultaneously. So that's important. We have to augment each sample with metadata. For example, a counter value. For example, it's important to know for an ADC sample on which position of the measurement it should be stored. And of course, again, I can't highlight this enough, interfaces are important. For each unit, we need clean interfaces. I go again for a simple handshake. So forward handshake, we get the data and a valid signal. So that's something that will solve a lot of problems. If that's not sufficient, add another signal where a unit signals I'm done with calculate. So that helps a lot. So how could this look like? I just draw some other method here, so some method, a sequence chart. So we get a value from the ADC. This ADC value is passed to an input handler, which augments it with an ADC value, with an index. So this input handler takes care of the counters. Then we fetch a value from memory, augment it again to these signals, and just add this together. Then we get our average value together with the index, and we can write it back to memory. So this deals with counters. Here we have things that handle memory access. Yeah, and this could be done if we use just block RAM each in one clock cycle. This means if we assume really we are in this scenario, we can put in new data at each possible clock cycle. So we have a maximum data rate of f clock frequency. So we are a factor of 5 faster than the finite state machine, just by changing your implementation. But here the point is that the latency differs from the throughput. So how long does it take for an item to process? Again, it's 5 clock cycles. So you're just optimizing one thing. And most probably this implementation will need a little bit more resources on the FPGA because of those metadata handling and so on. Still, it's often a good idea to go for a pipeline, but from my experience, please go for it at the point where you see that the FSM does not take you to go. Because it's a little bit harder to implement, and if you're starting off, then maybe not go for the pipeline in the first place. There are a lot of other things for pipelines. For example, what happens if one unit takes a cycle longer, but not always, but only in certain scenarios. There are really interesting things. If you want to know more about this, you can have a look at processor pipelines also in your phone, and each processor, the instruction processing is done in a fashion like this. Okay, just as a comparison here, for the FSM, we have a maximum data rate of f clock over 5. For the pipeline, we can go faster. Of course, we pay off with another RAM port and some other implementation structures. For an ASIC, or also for an FPGA, dual port RAMs are a little bit more expensive by means of area or FPGA resources. So they are quite big, or at least bigger than single port RAMs. Okay, the state machine needs additional state variables. We can verify it only in a monolithic way. You just have to verify it in just a single block. And but on the pro side is it's really easy readable code. So that's something which might fit on several, maybe on 2 pages of A4 paper. And that's something you can overview. For the pipeline, you have the overhead for interblock signaling. You have several blocks. The code size increases a little bit. It's not that easy to read, but you can verify individual blocks, and that's really cool. You can really check if each component does as intended. Even for an average like this, I would do verification on block level here, because eventually someone will come up with some new specification, some change in your system, and you have to make sure that still everything else works as expected if you modify something there. So please be careful about this. And it's easier to debug if you have an actual problem, then you just add another test for a specific block and you see what happens. Of course, the code can be a little bit harder to understand because you have several blocks and just one instance where it fits together. And yeah, it's just a matter of reading experience, whatever you have here in looking at this pipeline model. Of course, I again left out some things. So the actual realization, I won't show the individual blocks here. There is more to data formats. Of course, you are not always dealing with unsigned integers, and maybe you don't need all the time double precision floating point numbers, because they are again expensive to process. Timing constraints and clocking schemes, something to at least look up in the manual. I don't go into the tools, and if you have special algorithms like matrix multiplications and so on, there are already algorithms and patterns for that. To go into that would take me too far here, so it would take too much time. There are also trainings for that, for matrix multiplication. I had recently a training of 2 days. I can't compress it here, sorry for that. Also bus systems like Wishbone, AHB, and AXI. That's just something where you could follow up after this lecture or when you want to create your own design. Okay, general hints for implementation. I would always choose at first the pattern with the lowest implementation complexity. Just make things easy at first. Do not blindly implement, but test your code in simulation. Again, this is important. It's really hard if you programmed your FPGA and it works fine on your desk and you give it to a colleague, and somehow colleagues are very creative in using other people's tools and they do something you didn't expect. You will have a hard time debugging. And it's good to have a simulation there, and you can remodel the situation and just observe what's happening. It seems like extra effort, but it's worth the time. It's worth the time once you had the first thing you had to debug there. Choose your data formats wisely. Think about if you really need the full precision of double precision floats or whatever. This might get you out of several challenges when meeting area or resources in your FPGA. And you should compare your hardware to a Python prototype or whatever prototype, to a specification here. And of course, please do benchmarks and see if it really works and if it's really worth the effort. So now where to start? Now we have a brief overview, what FPGAs are, how to use them a little bit, and some ideas about implementation patterns. You can just get an FPGA board, install the software. For the smaller boards, the software is not open source, but at least free, and you can start coding with that. After Q&A and break, I don't know if we do it, let's see. We just look a little bit deeper into implementation practices and pitfalls. And this brings me to the end of my first part. of this lecture. And I'm open for any questions you might have.
So just to say that we will have a constraint is that the doctoral candidate presentation start at 11:05. And I think that some of the supervisors that are not there, they will connect to the Zoom.
Okay, so
maybe we can, and we have 1 hour and a half for lunch.
okay,
So maybe we can start, stop, and restart maybe.
yeah, okay.
Yeah, sorry.
So are there any questions?
Yes,
Yeah.
It's very simple. It's like, what is the clock cycle? So it is very relevant to data for something or understood.
For now we go for some practical things, and you will already see some code here. Still questions left? Okay. So motivation about us is actual coding is just a part of the work. Structure and experience are important. And always, not only experienced digital designers write this code. So you have to be aware of the basics. So how to do things right, how to do it wrong. And some pitfalls here that I tried to get things on the slides that you don't necessarily find in books. I collected some use cases from real designs. It's a little bit Verilog-centric. And my goal, as I put down here, is a slide set that you can review before starting your first design. So I might also skip some things to stay in the time frame. So I'm talking about good design practices. This means that are things that are somehow known to work. Basic schemes that you should follow always. If not, you'll have a hard time in coding debugging. If not, debugging will cause you to miss deadlines, and it may introduce additional new bugs. Some of the rules seem obvious. Some of them seem to produce effort, but you'll save the effort later. But one of the basic rules that applies nearly everywhere in your work, code should be easy to read and understand. For the reader, not the designer. There can be different persons. So good design practice starts with communication in your team. Talk to an experienced digital designer if you have one. If you need consulting also after this lecture, you can also send me an email, that's fine. But be prepared if there are questions. So what does this code actually do? How the initial states work? What's the clock speed? Are there internal clocks? Whatever. And if he doesn't ask you something and you want to tell him anyway, just do so. Okay, modularity in architecture. It would be also material for another training, but I just copied some things from the software guys, which I find also really useful here. Consider things like the separation of concerns. Or it's called single responsibility principle. Each block has only one specific purpose, not 10. Cohesion should be low, so functionality should not depend on too many additional blocks. It should be easy to test and to verify, also in unit tests. It should have clean interfaces and do not repeat yourself, so don't copy-paste code. You will mess up eventually. That's what every designer does. If you have the same code at 5 different places and try to update it regularly, it fails eventually. Okay. Sometimes it's also good to keep the implementation in mind. And now this is for the people who already wrote Verilog code or VHDL. Just by example, which kind of flip-flop is this? Technical informatics. So this means when the clock is rising, then we run this process. Or when the reset signal is rising. 1 to 1. If the reset signal is rising, A gets set to 0. Otherwise, it gets set to some arbitrary whatever value. So
A latch.
yeah, a D flip-flop. Call it a D flip-flop here. So with an asynchronous reset to be complete. So then we could have something like this. What's that? We have a process that depends on 3 different values asynchronously. The clock has priority. Independent of the clock is the reset. Only if the clock is not rising at this point. In every other case, we do something like this. I call this the impossible flip-flop. That's just a unit which does not exist at all.
What is a flip-flop?
That's a 1-bit memory.
Okay.
By real example, next thing would be something like okay, I'd like to wait here for 100 nanoseconds. Of course, you can't synthesize this because the FPGA with logic gates has no notion about timing or about time itself. It's just the gate processes its input data and you're done. Another impossible flip-flop. So I skipped this example, but the problem here is those constructs work in simulation, but not in the FPGA. So you will have mismatches between the simulation and the things that this thing is actually doing if you go for patterns like this.
Could you say why it works in simulation but not real?
Yeah, it adheres to, so it's no problem for a simulator to run this, to detect those 3 events and run this code. But mapping it to an actual flip-flop, that's difficult. Even if a synthesizer might try it, it will mess up the timing or some other point.
So actually that highlights the failure of the simulation tools. If the simulation can reproduce behavior that the physical device can't.
Yeah, I would call it maybe a non-convergence of simulation and synthesis there. But I think that's more historic reasons. So if you stick to implementations pattern like this, you just stay out of the area where it gets complicated.
Yeah, I guess the question is why the simulator can run this thing. Do you need it for something else? Is it needed for something else to have delays?
Yeah, it's needed, for example, if you want to write test bench code. So if you want to describe a sequence in your test bench, for example, apply signal A, then wait for 500 nanoseconds, then apply signal E. That's okay. That's also something you want to do in a simulation. But you shouldn't do in your synthesizable code.
Okay, so it's not a failure of the simulation, it's more the simulation has more freedom to let you test various capabilities.
Yeah, exactly. Yeah, thank you, Eric. Okay, I won't go through all of those details. Just have a look at the time. So things like, please format your code, use meaningful comments during the development, not after development. Keep them up to date. Do not comment code which is self-explaining. Or do not comment out code. It's just confusing to people. Keep your code clean. If you change something, make your code better. Every time you have a look at your code, you have the chance to make it better. Name your signals, name your states, and do not mix too much functionality because of single responsibility principle, and please be consistent in your coding style. That's not really academic, I know, but that's part of the practical things that make design just work. Maybe I do 2 examples and I skip the rest. So the quick test for code quality is, or the only absolute metrics is number of what the fuck per line of code. So something else is how many screen pages does your code need to show its functionality? It shouldn't be too much. So just some heuristics. You have to develop eventually a feeling for code complexity that fits in your colleagues' heads.
Do you have tools that tell you the overall complexity of the algorithms?
Sorry?
Can you estimate, like in terms of big O notation complexity for your code?
Okay. Of course, you can estimate this, but here I mean the complexity by looking at it, not the mathematical kind of complexity. It's just about how much time do you need to understand it. It might seem obvious to you, and also my code sometimes seems very obvious to me, but I have to explain to my colleagues, and that's an indication for I need to rewrite it. And also be kind to your verification engineer and future generations of designers that need to use your code. That's maybe the most basic thing that comes when this comes down. Format your code. That's something no one can read. That looks a little bit better like this. And another thing about comments, and then I'll let go of that. Describe purpose on a high level. That's not a useful comment there. Be specific in why you do something, not how you do it. And please keep your comments up to date. Something like this. What would you tell something about something like this if you find something in your colleague's code?
You prefer 0 over 1?
Yeah, whatever. And please use version control for that. If you comment out code, you are not trusting your version control system. Okay, so now I just skip forward a little bit to keep the time frame. Again, it's about writing beautiful code. That's something that always helps you. Good design practices about also tests. Never check a test bench by looking at waveforms. It should be self-checking. There should be test conditions. It's the only way of keeping it scalable. Eventually, you will miss something. That's just human. And self-check, a colleague once said, the computer doesn't get bored checking things hundreds of times. Use
Because I remember that you checked already.
Exactly. Write a simple test bench before you start coding and increase the test coverage step by step, and keep your test benches for later. Don't delete them unless they are really outdated. So it's like Python, please keep your unit tests. If you if the unit is still there, it should still be tested. And often it's a good idea to integrate your test benches in some continuous integration environment that you can keep track of your design, especially when it comes to larger design teams. Okay, why test at all? Verification is important, but the most evil thing is that your design might break due to some small change that seemed quite simple. So please check and monitor your design state. There are several kinds of tests. You can test individual modules, you can test the integration, and at the end you have some kind of acceptance tests where you tell, okay, that's the definition of I have finished my project. Okay, those architecture rules, by the way, they also apply to tests. Just saying, tests that test 10 different things are just not good. So now that's also something about design details to look up for you later. That's just something, I think you get the slides. Are the slides provided afterwards? Yeah, okay.
If you read.
Yeah, sure. Also think like, please do it that way, then you will have less problems. Okay. Code documentation. Someone once said, it's like working in the kitchen. Cooking and eating is more fun than doing the dishes. And the life hack I acquired from YouTube is, if cleaning is easy, the probability of doing it is higher. So the effort for the code documentation should be as low as possible. In general, document what you implement, why and what for, and why like this. Often there are 10 different ways to do it, and someone might need to know why you chose this path. And the non-obvious things are the interesting and important points. Please integrate documentation within your design. Also makes your life easier because it's always up to date and you have the matching version. Write your documentation in parallel to your code. It's something that I learned also the hard way. it's a little bit about discipline in design, of course. Tools for that can be Markdown. That's very really powerful. It can be versioned. It's easy to write with something like Markdown Preview Enhanced in VS Code, but which I also use to generate those state charts at the beginning. You can directly integrate this into your documentation. That's really cool. And you can convert it to Word or whatever favorite format you might have for final documentation of your overall system or data sheet.
The documentation, you have to write it by separate. You don't have like generic like tools that read the comments or the description from your code. And
yeah, the bad thing about hardware description languages, we are not at the point where Python, for example, is with auto documentation and just things which goes through doc strings. That's just not there yet.
Anyways, a question there, because I also noticed recently a lot of people are using automatic documentation tools from Python, and they're very good at documenting the interfaces. Now everything's connected, and they take the part that you write in the interface, format it nicely. But this has, to me, always been lacking, because that's just a documentation of the system as it is and what each function does. But what I'm missing is the actual main documentation. To me, should be, why was the architecture chosen this way? What are the fundamental design decisions? And this, I think, needs to be documented in a very different format than just doing it inside the code and then hoping for the system to convert it. Do you have any kind of best practices on how you document this really essential part, or you just do it individually?
So for my personal development, it's like this. I start off with a Markdown document where I just put my interface, the structure, and what brought me to this structure. And then I start implementing and add the detail about the individual blocks.
Okay.
And at the end, I strip this down and copy paste this to the data sheet, because that's our department, some more word-driven process.
Okay.
That's something that I found out that works for me.
This then basically becomes part of the repository where you also control it.
Yeah, and it's something which is also really important for me to have it right beside the code.
Right.
Not in the code, but beside it, so that you always have the matching version.
Yeah.
And there's nothing worse than code where I don't know what it does, and you have to fix something, and you're looking in documentation, and it's just half a year old and doesn't match anything in the code. Okay, other questions here?
Doesn't this sound like a job for the AI? Like looking at the code and then
Yeah.
then you can see what it spits out, and
well,
maybe
it will
correct
tell you why, though. It will tell you what
It
this
is.
is, and it will describe you what it does, but it won't tell you why did you choose this.
I'm not so sure that it would not be able to understand it.
No, it won't tell you why you chose this infrastructure.
Now we have to try it. I guess it depends on every piece of code. You cannot say, that.
I would propose an HI, so human intelligence experiment here.
Yeah.
Give a code to a student, which is knows the language, tell him nothing about the system, and let him document.
Yeah, I will show some curves where you guys can see the.
I know LLMs and so on are really powerful for that.
Yeah.
But they just extract your code. They might not get your original intent. So it makes sense to at least try to document it on your own. It's good to have a side-by-side view if the AI saw the same thing. That's interesting.
I'm just saying.
Yeah.
It will come. I suspect that it will come.
Of course. I'm also interested in this topic, especially for that, to see whether your code matches your documentation or also proposing some text parts there. Either it will frustrate the developer because it's so bad and doesn't match anything, so you write it. That's fine. And if it matches, that's also fine. So I can live with any two results there.
And just to comment on this, if the intention is important, the purpose, the AI will ask you. So you ask the AI to document, and then it will ask you 3 questions or 5 to describe your intention, and then the documentation may be perfect. If it's a really smart AI, it knows what questions to ask.
Yeah.
Depends on what you want.
Maybe not yet, but I think it will.
If we're coming to this point, it's again something. Did you write it down beforehand, or does the AI ask you? You will have always the point that somewhere you have to document your initial intent. Okay. Then I just proceed to some things. I might also try to skip. there are some pitfalls here. For example, it's possible to write combinational loops, so endless loops which run in 0 time. Sounds crazy. In circuit level, that's something like a ring oscillator. Yes, so you have a feedback which just runs as fast as possible, and it will crash normally your simulation, and therefore it's hard to debug. I put an example here that you know what to look for. If you're once in the point that your simulation just stops at some point in time, look for something like this. Latches, please explicitly put latches only where you intend to do it. If you are unsure whether to place a latch, just don't do it. Then place a flip-flop. So 1-bit memory, which is always clocked. Yeah, I said before, delays are not really synthesizable, so please don't use them in your synthesizable code. If you're writing to a variable, please do it only in one process, not in 2, because then you have 2 drivers on the signal line, which is a conditional short. It will consume a lot of power and cause a lot of problems. And there can also be the case where you have some input signals to your blocks that you don't want to connect wherever. Please connect them somewhere. In the worst case, you get some floating output. This means it's some random value which is not constant over time. And that's something really bad to find in your system. Okay, my last point here is about version control and bug tracking and so on. So first is, where do I need version control? For code review, also sometimes for blaming someone with a bug. So you introduced it here, please fix it. And track your process. Or better question is, I also have often, why did it actually work yesterday and what did I destroy today morning? Also, it's important for code distribution, when you want to distribute your most recent code version. And of course, for releases and continuous integration checks. That's really important to see whether your software or your hardware still works. Basics of Git. So the short lesson here is, please use it. If you don't know how to use it, please have a look into it. It will save your life several times during your PhD. It did it for me, and I went wrong before. I don't want to do this again. Then there's something, if you want to if you have a colleague in digital design, please describe your requirements, write notes on his to-do list and so on, give meaningful names, track process and so on. But if you have an issue tracker there, that's a tool for organization, but not for communication. Please don't stop talking to people there just because you put an issue on the list. Then there's another thing about continuous integration. I talked a little bit of this before, where you have a batch of test benches running on your design, checking if everything works as intended. Please do this on a regular basis with a schedule. Then you recognize errors shortly after you introduce them or someone introduced them. And this means you can fix them easier in most cases. In GitLab, this means you need to define some YAML files and so on, and the run schedule if you are unsure on how to do this. There are many tutorials. Take the time of looking into this. It pays off quite shortly. Prerequisites, of course, are self-checking test benches and run scripts. So you can't do every night a check looking at your waveforms. That's just something that doesn't scale at all. So this brings me to the end. I hope we have still at least 2 or 3 minutes for Q&A afterwards. So FPGA development exhibits potentials for fast execution, for parallel algorithm, for real-time processing and direct stream processing. But you have to invest the additional effort. Issues from software development like code style architecture and so on, they're as important as in software, if not even more for hardware. So it's about design flow, about simulation verification. And of course, you have to invest the effort of bringing up a hardware platform. I've only shown some common challenges. There's more to this. I can just motivate you on to try it if there's a possibility. It's a really interesting field to work on, and many algorithms can be made more efficiently when you place them on programmable hardware. And maybe you eventually want to go for an own chip with your algorithms. You want to integrate it into an ASIC, where you have even more performance. But then an FPGA is a very good starting point, because describing a digital circuit for a chip, it's really done in the same way as describing it for an FPGA. Yeah, the differences are quite minor. For example, memory access and so on, but this can be mitigated. And if you ever plan for going in the far future for an ASIC implementation, have a look at FPGAs. Okay, that brings me to the end. If you want to, please note down my mail address and phone number. And if you have a challenge there, you can always drop me an email, and maybe I'm able to help you. Thank you. I'm open for questions that you might have, as long as we have time for that.
Yeah, thank you.